So let's actually prove it. Our first contradiction proof. I'm so proud of you guys. So proof. And I'm not going to write the formal statement because this is the formal statement. I just kind of combined them. Proof. So first of all, you always tell your reader, if you're doing an indirect proof, tell your reader what you're doing. So proof by contradiction. If you're doing a direct proof, you don't have to say that. You can just get started. But for indirect proofs, always good to say this. So now, assume for contradiction that there exists an N and Z, or actually, I'll do even better, that the claim is false. Now we say assume for, actually, you could also say the sake of contradiction if you want. Assume for the sake of contradiction. All it's saying is that if someone looks like, why would you assume this? Or assuming it to try to get to contradiction. We already said proof by contradiction. We're just being redundant here. Just let everyone know we're not saying this is true. We're actually saying the opposite. But anyway, yeah. So assume for the sake of contradiction, the claim is false. Thus, there exists an N and Z such that N is even and N is odd. Then, now this is great, but making this assumption we now have a foothold. Then, by definition of even, N equals 2k for some k and z. Also, similarly, I've gotten so used to saying similarly the way it's spelled, like similarly, that I don't like that now I can't say it right. It's like the people that say Wednesday instead of Wednesday. The point is I'm trying to break the habit. So I'm gonna use a lot of similarities this time. But anyway, similarly, by the definition of odd, N is going to equal to t plus 1 for some t and z. Now, again, we said it before. Let's say it again. I'm actually really proud of you guys in your homework 6 because no one fell for this trap so far. But it's important that k and t are different here, right? Because we just know it's even and odd. We don't know that the k is going to be the same, right? So if you're talking about two different things, use two different variables. Yeah. Thus, N, or I'll say 2k equals N, which equals 2t plus 1. Hence, 2k equals 2t plus 1 by the transitive property. Transitive because of 2k equals n and n equals 2t plus 1. The transitive property tells us 2k equals 2t plus 1. And then next from that, we can get that 2k minus 2t equals 1 by subtracting 2t from both sides. From algebra, we know that we can always subtract the same thing from both sides and the equation's still true. Now here, this is going to be, we can factor this. So this is true by factoring. And then this only happens if k minus t equals 1/2. This implies k minus t equals 1/2. We can get that by dividing 2 from both sides. And I'll say here note 2 does not equal 0. The only reason you're noting that is because you can't divide by 0. And so whenever you're dividing, you have to make sure you're dividing by isn't 0. It's really obvious here. Sometimes not so obvious. Yeah. So we just proved k minus t equals 1/2. And this should be a problem, as we already talked about, because k and t are integers, so k minus t should be an integer. Note, since k and t are in Z, and Z is closed under subtraction, k minus t is in Z. Thus, 1/2, which equals k minus t, is in Z. And this is the beautiful part. We have just proven something ridiculous that we know is wrong. We started with an assumption and logically show from that assumption that something incorrect is true. Therefore, that assumption must not be the case, right? So this cannot be true, right? And we put a little arrow here. We put 2 arrows going against each other because that's kind of like symbolizes contradiction, like 2 things going against each other. And so we say contradiction. I like to put exclamation points. Technically, everyone I talk to tells me not to, but I don't care. Okay, I like it. I will put it in the mathematical proof. If you're good enough, we'll let you do it. Contradiction. 1/2 is not in Z. Therefore, our assumption is incorrect. Thus, for all n and Z, n can't both be even and odd square. Done. You guys can't see that. Now you can. How is that? Come on. That's pretty good, right? This is a absolutely, totally formal, rigorous proof that numbers can't both be even and odd. Something that's so obvious, but so hard to prove. But we just did it. And the way we did it is brilliant. It's not by going at it directly, right? It's by kind of being a little coy with it, right? Going like, okay, assume it did happen. And then show that leads to ridiculousness. It leads to 1/2 being an integer, which it's not. I mean, this is like, I mean, you can use it for anything. It's not even a math thing. It's a lawyer thing. It's a philosophy thing. Like imagine, I went over to my friend's house and the grandma made some like disgusting peanut butter salad, right? And I was like, oh no, I'm sorry, I can't eat that. I have a peanut allergy, right? And then like 2 days later, you see me gobbling down a PB&J. Right. The point is, if they were like, if the grandma was like, oh, he has a peanut allergy, but actually, wait a minute, I saw him eating a peanut butter and J, that contradicts the peanut allergy. That's not a good example. The point is though, if you assume an incorrect thing and then prove it leads to ridiculousness, that proves it's incorrect. Any questions? Is this making sense? Good. Good. Come on, this is kind of cool, right? Oh, you wait. You don't think it's cool now, you just wait. All right.